Hello, this is Mr. P, and today we're going to learn verifying trigonometric identities, which is one of my favorite topics. Uh, to start out, though, we do have to stress that we cannot assume the two sides are equal. This means that we can't do any operations that cross the equal sign. In other words, we can't add or subtract to both sides, we can't multiply or divide both sides. What we can do is manipulate one side at a time until it's the same as the other side. This would be the proof that the identity is valid. And we usually want to start with the more complicated side because it's usually easier to destroy something through cancellation than it is to build something that wasn't there to begin with. And the most important thing, though, is you must keep your goal in mind. In other words, when you're manipulating one side, look at what you're trying to manipulate it to and pay attention to the number of terms, the types of functions, etc. That way you're always working towards your goal. There are certain things that we can do. We can look for cancellation opportunities. We can use identities to rewrite expressions, especially the Pythagorean identities. Those are very good for exchanging monomials for binomials or vice versa. If worse comes to worse, we can always convert into sine and cosine. Sometimes the algebra is a little easier that way, and also we get some cancellation opportunities that seem to pop up. We could either factor or distribute, but you want to make sure you do the one that gets you closer to your goal, paying attention to the number of terms, function types, etc. Same thing with either combining fractions with a common denominator or breaking them up. You want to do the one that gets you closer to your goal. We can also multiply by the conjugate, which is an often overlooked strategy. This helps us to take a binomial denominator and turn it into a difference of squares, which then we can usually switch out using a Pythagorean identity, and we'll have a monomial in the denominator. We can also creatively multiply by 1 or add 0. This is a more advanced tactic. Adding 0, for example, we could add something that isn't there and then also subtract it so that the net effect is 0. But by adding it, we're able to group some terms and do a substitution using an identity. So it gives us more flexibility to play with the terms. Now, the intimidating thing about trig identities initially is students just don't know what to do next. And you can take some of the fear out of it if you realize there's only a finite number of things that you can do in the first place. So if you're aware of your options, then you can start making choices that get you towards your goal. This is the mindset you should have. But above all, you do have to get your hands dirty. Try something. Make a change. Look for the cancellations. Manipulate it some way, and then see if that's getting you towards your goal. So let's jump in with some examples. We're going to start by verifying this identity. The left side is definitely more complicated than the right, so I will start with the left side. And I'm actually going to show two different methods for verifying this identity. And it's important to realize that there's no one right way to verify the identity. You do have options, but you always want to be working towards your goal, and you should arrive there as long as you don't make any algebra mistakes. So, of course, in the first one, I'm going to start with the left side, which is the secant squared minus 1 over secant squared. And I should recognize that secant squared minus 1 is tangent squared. So I'm going to make that substitution in the numerator. And then for clarity, I'm just going to break this up a little bit for clarity. Tangent squared over secant squared is the same as tangent squared times 1 over secant. And now looking at my right side, looking at my goal, I realize that I want sines, and neither of these are sines, so let's change everything into sines and cosines, and hopefully our cosines will go away. So tangent, if I change that, tangent becomes sine over cosine, and the reciprocal of secant is cosine, so I can rewrite it as cosine squared over 1. This brings up a nice little cancellation opportunity where the cosine squares cancel each other out, and we're left with just sine squared, which is what we were looking for in the first place. Now, a lot of students get down to either this step or this step and they're not sure what to do next, well, look at your goal. If you want sines, then you need to start changing these to sines and cosines. Well, if we look at another way to do the problem, let's start with the same left-hand side. And this time I'm going to break it up into two different fractions. We have a monomial on the bottom, so we can do that. On the left fraction, I'm going to have secant squared over secant squared, and that'll be minus 1 over secant squared. And then some simple substitutions. Secant squared over secant squared is 1, and 1 over secant squared is cosine. And then you should recognize that as a Pythagorean identity. 1 minus cosine squared is sine squared, and we arrive at the same goal. Notice how it didn't matter which way we went, we eventually were able to verify it. So with all these problems, there's definitely more than one way to work these problems. You just want to make sure you're working towards your goal and making the right decisions. All right, let's look at some more examples. All right, when I first see this one, I obviously see the left side is the more complicated side, so I'm going to start with the left side. But I do notice that there are two terms on the left side, whereas the right side is just one term. So there's a good thing to start with. Let's combine the fractions so we have a single term. And to combine fractions, you need a common denominator. To get a common denominator, I need to multiply the different denominators. So if I multiply those two binomials, you should recognize the pattern as a difference of squares, and the denominator will become 1 minus sine squared. For the numerator, I have multiplying the top and bottom by 1 plus sine, and over here multiply top and bottom by 1 minus sine will give me this as my numerator. And although we weren't specifically trying to do it, we do have a nice little cancellation opportunity that pops up. And this happens a lot of times when you are working towards your goal, usually good things happen. And here, plus sign and minus sign, they cancel each other out. So my numerator becomes 1 plus 1, which is 2. And then I can recognize 1 minus sine squared is cosine squared. And I can bring it out of the denominator into the numerator by reciprocating it. So this is the same as 2 times secant squared, which is exactly what we were looking for, and the identity is verified. If we look at number 3, we have definitely a more complicated left side, so I'm going to work on that one. The first parenthesis is exactly a Pythagorean identity, so tangent squared plus 1 is secant squared, so I make that substitution. The other parenthesis is almost an identity, but the identity is sine squared is 1 minus cosine squared. So I want to change the order of the difference there. I can do that by factoring out a negative. If I factor out a negative 1, then I change the order of the binomial to be 1 minus cosine squared, which is what I was looking for in order to switch it out for sine squared. And now again, students might get to this point and say, okay, but what next? Well, look at your goal. Your goal is tangent, so you know that tangent is sine over cosine. I have a sine, but I need a cosine. So I don't want secant, I would rather have the cosine version. So instead of secant, we substitute it with 1 over cosine. And then I can do the multiplication, which gives me negative sine squared over cosine squared, which of course is negative tangent squared, which is exactly what we were looking for. All right, number 4. Now, when I first see this one, I see many different functions. I have tangent, cotangent, secant, cosecant, a lot of different functions. So this is a good candidate to switch everything to sines and cosines and try to get the cancellation opportunities. Well, if we change tangent into sine over cosine and cotangent into cosine over sine, then we can get started. I chose to work on the left side because I had 2 terms. I could have started on the right. It doesn't really matter either way. This one, though, we will work the left-hand side. Now, unfortunately, we didn't get any cancellation opportunities, but I can also notice, looking at my goal is 1 term, and here I have 2 terms. So if we add the fractions and combine them into a single fraction, then we'll have one term. So I need a common denominator, which is cosine times sine. And when I multiply the left top and bottom by sine, the right top and bottom by cosine, I end up with this fraction. And we get a nice little cancellation opportunity here. Or in other words, we can use the Pythagorean identity that sine squared plus cosine squared equals 1. I wasn't specifically trying to do that, but very often when you're working towards your goal, good things happen. So sine squared plus cosine squared equals 1, so I make that substitution. And I also want to notice that I do want secant and cosecant, so I'm going to break this up into 1 over cosine times 1 over sine. And 1 over cosine is secant, 1 over sine is cosecant, so we have exactly what we're looking for, and the identity is verified. Okay, number 5. This one we can work on the left or the right. I'm going to choose the right because then I get to use the often overlooked strategy of multiplying by the conjugate. The denominator is 1 minus sine. If I were to multiply that by its conjugate, I would create a difference of squares, which I can then switch out using a Pythagorean identity. So I'm going to multiply the fraction by 1 plus sine over 1 plus sine. This could also be considered a creative use of multiplying by 1 or multiplying by the conjugate. In this case, our goal was to get the bottom to be 1 minus sine squared. And on the top, we had a decision. I could have left it factored or I could distribute. I chose to distribute because if we look at our ultimate goal, it's 2 different terms. So ultimately, I want to break this fraction up into 2 terms. So to do that, we are going to need to distribute eventually, so I went ahead and distributed in that step. Now the 1 minus sine squared, we should recognize that is cosine squared. And nothing changed in the numerator. But now, like I said, I want 2 terms. I have 1 term, so let's break it up. When I do that, I'm going to get cosine over cosine squared plus cosine sine over cosine squared. Brings up some nice cancellation opportunities. This cosine cancels out one of them in the bottom. This cosine cancels out one of them in the bottom. And it simplifies to be 1 over cosine plus sine over cosine, which is secant plus tangent, which is exactly what we're looking for. Okay, number 6. I'm going to do this one by working both sides because it's not against the rules to work on both sides. You just have to do it one at a time. You can't use operations that cross the equal sign. So notice how neither of these are simplified form. So what I'm going to do is I'm going to simplify one of them to see what we get and then see if we can simplify the other side to the same expression. Now first of all, if I look on the left, I see a cotangent and a cosecant, whereas on the right there's only one function on the right. So I want to make one function on the left. So I'm going to switch out the cotangent because that's the one squared, so I can use the Pythagorean identities. I'm going to switch out cotangent for cosecant minus 1. And the denominator stays the same. I should recognize the difference of squares in the numerator, so I factor that to cosecant plus 1, cosecant minus 1. And then I have a nice cancellation opportunity. Cosecant plus 1 is the same as 1 plus cosecant because the order doesn't matter in addition. So those 2 can cancel, and that leaves me just cosecant minus 1. Now I stop here on the left side because this can't be reduced any further. This is the simplified form. So let's try the right side and see if we can simplify it to the same expression. Now notice how our goal on the right side is no longer to make it look like this, which is what we started with. We now want to make it look like this. This is our new goal. So judging it that way, we can see our goal is 2 terms. So I want to take this 1 term and break it up so that we have 2 terms. So that's an obvious first step, is break up the fraction. I can do that because we have the monomial in the bottom. So I break it up into 1 over sine minus sine over sine. And then, of course, 1 over sine is cosecant. Sine over sine is 1. So we get exactly what we're looking for, which is cosecant theta minus 1. So the left and right side both simplify to the same expression, so the identity is verified. Okay, for the last example, we have a two-parter here. It would definitely be easier to simplify the more complicated side. In other words, to work with the more complicated side. Here I would obviously factor out tangent squared. That would leave me secant squared minus 1 in the parenthesis. I can switch that out for a tangent squared, and then I would have tangent to the fourth. That's pretty straightforward, pretty easy. But where I'm actually going to work this the other way to show you that it's a little harder and a little more creative to go from the simplified form to the complicated version. And the reason we're doing this is often what you'll see in calculus is you'll have an expression like tangent to the fourth, and you'll need to change it into an expression like this so you can do things such as integration. So if I take tangent to the fourth, the first step is I'm going to break it up into tangent squared times tangent squared, which is a completely unobvious step. Reason I did it is so that I could have more options to use the Pythagorean identities if I have the squared. And that's what I'm going to do next, is instead of tangent squared, I'm going to switch it out for secant squared minus 1. And then finally, if we go ahead and distribute that tangent, then I'm going to end up with tangent squared, secant squared minus tangent squared, which is exactly what we were looking for. It's not a complicated identity to verify. It's actually pretty easy. But that first key step is not a very obvious one. And we have the same thing with B. The first key step is the unobvious one, and then it's pretty straightforward from there. I'm actually going to take this expression and reorder it. With multiplication, the order doesn't matter, so I'm going to put the cosine first. Then I'm going to break up the cubic into a square and a linear. So that way the squared portion, the sine squared, I can then switch out for 1 minus cosine squared. So I reordered them so that I could make the substitution. And now if I distribute, then I can get exactly what we were looking for. As long as I avoid the common algebra trap of cosine to the fourth times cosine squared is not cosine to the eighth. Remember, when multiplying powers, we keep the base and add the exponents. So if you do the algebra right, you will get the correct expression, which is what we were looking for. And we're done.